And in this session, there will be two papers presented. Separation logic-based verification atop a binary compatible file system model, presented by Mihir Mehta from the University of Texas at Austin, and optimization of timed scenarios, presented by Neda Saedloy from Towson University in the US. So we'd like to start with Mihir, and you will have 20 minutes for your presentation. And if people have questions, they can put it on the Slack channel or on the chat here, and we'll be answering the questions soon. So, Mihir, please.
All right. Thank you for the introduction. And just a quick sanity check to make sure that everyone can hear me and see my screen. And I'm assuming everyone can. So let me go ahead with my slides. Yeah, thanks for showing up to this talk. I am going to be talking about some work that has been done recently using the ACL2 theorem prover to verify file systems and use separation logic to verify programs that make use of file systems. This is joint work between me and my advisor, who are both at UT Austin, as you can see. So, the motivation of this work is programs need verification, and program verification has come a long way in several different respects, but it's still tricky to verify the interactions of programs with the file system. And to take only one example of where programs can be tricky to verify, you have shell scripts which run all the time, and often there are multiple programs in a shell script which are interacting by means of the file system. The file system becomes a substrate through which data is exchanged between different programs, either synchronously or asynchronously. So that's just one of many different examples. And that is kind of what motivates us to try to make a model of a file system and try to verify programs that use it. In previous work, we built up a binary compatible model of an existing file system, which is FAT32. And this paper is intended to show how we use something like that to verify programs. So there are multiple ways of approaching this problem, but we decided to make our focus the notion of binary compatibility, and we picked FAT32, which is a fairly commonly used file system. You probably have pen drives around your home and office which still have FAT32 on them, as well as embedded systems which still make use of it all the time. And we decided to make a verified implementation that we can verify programs on top of. Uh, Using this, we deliver the following. We have the two models, low fat and high fat, which refer to low level of abstraction and high level of abstraction. So there's a formal refinement relationship between the two, in that low fat refines high fat, and this is something that's proven. And what's more, we have something called AbsFAT, which is a separation logic model of FAT32, which aids in reasoning about programs by representing system calls in terms of separation logic, and hopefully providing simple and clean specifications of these system calls. So to explain this, I need to provide a little bit of background about abstract separation logic. It is a variant of separation logic which reasons about slightly more complex data structures than vanilla separation logic. In in the former, we have, if you think of it purely from the point of view of theorem proving, you have a set of bindings from locations to values, and these values are usually what we might consider simple values, such as integers, strings, indivisible values in a certain sense. When we move on to structured separation logic and in turn to abstract separation logic, we first add bindings from locations to data structures. So now we no longer just have simple values, but we have data structures. and that's called structured separation logic. And when we move on to abstract separation logic, data structures are allowed to have holes. These holes are filled by variables, and those variables are in turn bound to substructures. So this is a very natural way of thinking about, uh, any kind of complex data structure that you might want to represent. But especially for file systems, when you're thinking about things such as directory trees, and you may sometimes want to consider a directory tree in isolation from all other, you know, directories and subdirectories inside the file system. This kind of thing is really helpful, and it helps you specify your system calls, which is something I'm going to show an example of in just a few slides. So here's an example of what it's like to represent a system call in abstract separation logic. We have consider mkdir. There's a command line version of mkdir, which is not the one I'm talking about. I'm talking about the POSIX system call, which, given the argument path, I attempts to make a directory at that path name, and either makes a directory or returns an error code explaining why it couldn't. There are several possible error conditions that can occur, uh, and some of the reasons for those errors might be that, for instance, the directory name at which you're trying to make the new directory does not exist, so there's no place for you to make a new directory, or something might already exist where you're trying to make a directory, which is again a problem, and so on. So this is the kind of thing where if you try to make a representation that handles all the possible cases that can happen in doing something as simple as mkdir, the complexity of any kind of reasoning that involves multiple file operations grows. And so let me show you a snippet of like a longer description of mkdir, which is in the paper. I'm showing you only two of the multiple Ho triples that go into representing mkdir, but I believe they are instructive. So in this Ho triple, just like all other Ho triples, we've got a precondition and a postcondition. And what this shows is a success condition for mkdir. So when we are calling mkdir, we get a return value which is stored in the variable r. And the fact that r is 0 in the post condition shows that we have success in terms of what has happened in mkdir. And consider the rest of this whole triple. Uh, what this statement here says is that the variable path resolves to uh, a path name P followed by a name B followed by a name A. So what this means is that P slash B is the directory where we are trying to create something, where we're trying to create a new directory, and A is going to be the name of that directory if that is successfully created. And what this other precondition says is that we have somewhere in our separation logic representation, we have the contents of B. B can contain C, which we don't care about. C is the rest of B. But crucially, the predicate can create A is true. What that means is that there is room to create A. This rules out a whole lot of error cases in which either B did not exist or A already exists as a directory or regular file. So this precondition rules out every single way in which things can go wrong. And so in our post condition, we have that the contents of B remain unmodified as far as C is concerned, C being the rest of the contents of B. And where we used to have room for A, we now actually have A itself. And the square bracket notation here indicating that A is now a new directory with no contents inside it. So that's one possible behavior of mkdir. But obviously there are others because, as I said, we ruled out a whole number of error conditions here. So what else could be happening here is we might, for instance, have everything remaining the same, but a file called A already existing and being bound to a string representing a regular file, which has textual contents. So if A already exists with some text held inside A, then obviously we can't create the new directory R. And so then we are going to instead return an error, which in POSIX terms is called exist, in that the file you're trying to create already exists. So these are two of the possible behaviors. There are all other errors that can also take place. And so this kind of thing is what persuades us to think that maybe this kind of representation is good, because at every step we are saying, well, everything else which is aside from what's held inside the contents of B is irrelevant. So we don't need to update any of that stuff in our state representation. We can leave all that as is. The only thing we need to update is the variable alpha p, which refers to the contents of B. And so yeah, we have a clear logical separation, and we therefore start finding it easier to reason about sequences of operations. And this, by the way, is true not just in terms of what I'm showing you on the slide, but it's also true for the theorem prover. The theorem prover finds it easier to do things if it doesn't have to update state representations in sort of a deep way, in terms of having to replace every single thing. If it can just be told that it's okay to update just this part of the state representation, the theorem prover has an easier time. And so we have at this point we have a pretty much complete implementation of high fat, low fat, and AbsFAT, and a number of useful system calls. And as I mentioned before, we have a refinement relationship between low fat and high fat. We also have a refinement relationship between high fat and AbsFAT, which is necessary for us to say anything about what's happening in the real file system. And yeah, low fat is efficient, it is tested, and we have a foundation for carrying out proofs of simple programs relying on AbsFAT, one of which I'm going to show in just a moment. So yeah, to fill in a few details about high fat, it's so far I only referred to it as an abstract model of low fat, but really what it is a tree model of FAT32. It retains all the file level metadata but not the volume level metadata. It's relatively simple to reason about file operations in this model, because we are crucially freed from some burdens which relate to allocation, space management. We don't have to worry about all these things. We just need to worry about whether we are accessing a file or creating a file or deleting a file. And read over write properties are much simpler to prove in high fat. And it's also been a practical experience that in as much as we had some bugs in this file system, though we've tried to avoid them and even remove them during the process of theorem proving, they were easier to locate and fix in high fat. Low fat is a disk image model. So this is where we have the real truth of the property which we call binary compatibility, in that it retains every single bit of data and metadata from the disk image, and it is held as an efficient data structure. So ACL2 has special support for things called single-threaded objects, which allow you to get some benefits which might not have with an ordinary object, in that array operations can be really fast, accessing and updating operations can be really fast, and since we are doing a lot of those kinds of accesses and updates when we are dealing with disk images, this kind of thing is important. Uh, this is binary compatible, and at each point, the disk image is in a state that can be read by other FAT32 implementations when it's written back to the disk image. And this is demonstrated by co-simulation with multiple implementations of FAT32, which we consider canonical. We have, of course, a refinement relationship between high fat and low fat. And so, what when we the next thing to do is dig into AbsFAT, which I've given you like a brief flavor of when I showed you these whole triples. But in AbsFAT, what we have is an abstract separation logic model of FAT32. in which once again we get rid of a number of details from low fat which relate to space allocation and space management, and we represent the file system as a collection of variables which are bound to directory trees which may or may not have holes. There are two logical operations that go into implementing system calls. They are called abstract allocation and abstract deallocation. When we have something like these two operations happening, we change the representation without changing the underlying file system. Respectively, when we are doing an abstract allocation, we are creating a hole within a directory tree and binding a new variable to the contents of that hole. And deallocation is pretty much the reverse of that, in that we take a hole that already exists and we fill it with the contents of the corresponding variable, removing it in turn. And that leads to simple representations of the file system state. So, what does it really take to prove that AbsFAT is correct? Well, AbsFAT is because it's at some levels of abstraction from the real file system, we need to think about what it means for it to be well formed. uh, what it means in terms of being well formed is that intuitively, whenever you have a frame in abstract separation logic or in abstract to be particular, you, you should be able to collapse it. And collapsing is something that I'm going to come to in a moment. But collapsing is something that's defined as the transitive closure of a binary relation. This is an awkward thing to talk about it, and it is also awkward for a theorem prover to work with. So part of our proof effort was getting rid of this transitive closure. So absfat gets rid of the existential quantification which comes from the transitive closure, because we are no longer talking about there existing something which we can get to by means of doing several steps. Instead, we're talking about something concrete. And the price of this simplification in sort of logical terms is that the evaluation of the file system tree is not exact, because there's no ordering imposed on these variables. We at no point try to say what order these variables should be in, because that's not a notion that makes a lot of sense. And so files can be rearranged within a directory. But then again, that is not really something that needs to bother us either at a conceptual level, because we are generally not used to thinking of files in a directory being ordered. And indeed, most file systems make it very clear that they do not have any semantics for expecting files in a directory to be ordered. So we also, and beyond the conceptual level, also at a pragmatic level, we don't have trouble with this, because ACL2 has a lot of support for equivalence relations, and we've already had to handle this issue of rearrangement of files within file system trees before. So we already have this kind of infrastructure for it, and we are not struggling with it anymore. We decide, when we are working with AbsFAT, to always think about file system trees modular rearrangement instead of them being completely pinned down to one specific ordering. And so what what we have in terms of proof so far is that a well-formed absfat frame always collapses to an instance of high fat, which is what it means for absfat to refine high fat. We also have proof that abstract allocations and deallocations do not modify the high fat instance we collapse to, and that AbsFAT implementations of several system calls have exactly the same effects as the high-fat implementations of those calls. So here's an example of what we get in exchange for all this labor of proving refinement relationships. We get proofs like this one. Uh, Consider what I'm showing you in this whole triple here. We have an mkdir operation followed by a start operation, and the return values of these two operations respectively go into the variables r and s respectively. So assuming absolutely nothing in the precondition, which is what it means to have a precondition of true, we get a post condition saying that whenever R is 0, meaning mkdir is successful, we know that S is also going to be 0, which means that the start operation is also going to be successful. This is a proof which illustrates the point of several kinds of case splitting coming up during its uh, resolution, either by hand or in the theorem prover. And that kind of case splitting should be intuitive from what I showed you about mkdir a few slides ago. In that a fairly simple operation which does nothing but create an empty directory can split into several cases, and so it is with start. So when we prove something like this, we actually have the theorem prover taking care of all these cases in a fairly automatic way and saving us from the trouble of having to reason about those cases manually. And so that is the kind of success we have. AbsFAT is successful in iterating through these cases and completing the proof without the need to manually instantiate lemmas. So code proofs are probably all fine, but most people will probably want to have something more in order to be confident that this file system this file system model is accurate and is therefore valuable. And so we have a series of co-simulation tests which check to see if the system actually works like existing mature implementations of FAT32 do. These tests are all written as ACL2 programs. Each of them replicates an existing program either from the co-utils or from the mtools. The co-utils are probably familiar to everyone because programs like ls and so on, which you use every day, come from co-utils. The mtools are probably slightly less familiar, but they are also considered to be a canonical implementation of FAT32. They are developed by GNU, the same people who develop the co-utils. And so co-simulating against them is something that gives quite a good degree of confidence that these implementations are correct. Each of these tests compares the results of running the canonical program against a test program. So for programs which produce output, well, it's fairly simple to compare the output of our test program against the canonical program with diff. And for programs which actually change the file system state, we've got a slightly stronger challenge, because we actually end up having to develop and use our own tool, compare disks, which compares entire file system volumes and disregards rearrangement of files. So this is where the two things tie together, in that the effort of making the infrastructure that disregards rearrangement of files comes in handy, both in terms of helping us with abstract separation logic, as well as doing co-simulation with real implementations of FAT32. And we have a number of tests for each one of these programs that we are co-simulating. They cover quite a wide spectrum of things that we might expect programs to do in terms of their interaction with the file system. So we have, for instance, read-only operations like stat and wc. uh, Although WC is not does not WC is a somewhat complex program which does actually looks deeply inside the contents of a file, not just to see that it exists, and counts its words and so on. We also have programs that remove files from the file system, such as unlink and rm. We have programs that make changes to existing files, such as truncate, and all of these are co-simulated successfully. It is the same with a number of programs from mtools, which pretty much do the same kinds of things that the co-utils programs do, but are still useful to co-simulate. So, having talked a little bit about AbsFAT, I also feel the need to mention some recent progress, which actually happens to have occurred after this paper was written. We now have verified low-fat primitives for every single thing we do in our syscalls, which is reading, removing, and replacing files. So this is an efficiency improvement over previous iterations of this work, because earlier, just to claim that we had verified execution, we actually needed to transform high-fat instances to low-fat, and prove that those transformations were correct. And that was fine as far as proof was concerned, but it did come with certain kinds of performance penalties. So now we no longer need to deal with those kinds of performance penalties. We can just do everything in low fat, and it is still possible for us to do proofs in high fat and AbsFAT because of the refinement relationships that we have, but we no longer literally need to drop down into those models. And this in turn allows us to think about what it might mean for us to explore concurrency, because concurrency is inherently something which involves multiple things happening at the sort of block storage level at the same time rather than at a completely abstract level. And so if now that we have everything happening in low fat, we've got room for a concurrent implementation of these primitives, which in turn sets us up for concurrent implementations of our syscalls. So where we intend to go with this work in the future is there's a few possibilities, and there's going to be some kinds of decisions that have to be made about which one is the most promising. But it does seem like it would be worthwhile to try making a fuse interface to the Linux kernel, because so far we have a number of POSIX syscalls, but they are accessible only from within ACL2. So in order to broaden the scope of this and actually have real code running on our file system, we might want to make a fuse interface which basically allows us to make a new file system without having to make a new kernel module. There's also a possibility of integrating with existing work on verified execution of C code on the x86 architecture. So this is some work that already exists for ACL2, and so this has been an integration that has occurred to us a few times, because this would sort of make a really strong pipeline for verified execution, or rather a longer pipeline, in that we are not just thinking about programs that execute completely in memory, but now we can think about programs that interact with the disk as well via the file system. And finally, we would like to explore concurrency issues for which you may or may not be using an oracle model of non-determinism. I mean, the oracle has proven useful in the past for verification efforts with ACL2 and other interactive theorem provers. So that is something which we are considering exploring, whether or not we can get to modeling concurrency in our low fat. And so that is pretty much the end of what I intended to say about this paper. I hope you will read it because there's a lot more detail in it. And yeah, I welcome any questions.
Okay, thank you, Mihir. We were a bit over time, but we have time for a few questions. If anyone can want to ask on the chat or on the Slack channel. Well, while the people think about questions, I have one question.
Sure,
Theorem proving for me, it's always been kind of mysterious and
sure.
difficult. So I'm impressed by the work you've done.
Thank you.
Um, but implementing FAT32 seems to be awfully complex. And my question is, how long did it take you to implement that and to verify it using the theorem proving mechanism?
Uh, I mean, this has been my project for a while, and this is not the paper we are talking about, is not the first paper that's come out of this effort. So, I mean, I honestly struggle to answer this question because I would struggle to draw a line between what's strictly implementing FAT32 and what's additional, because you could argue that abstract separation logic is not part of FAT32. So whatever you did with abstract separation logic is something which you did to help yourself in terms of code proofs. But I will say that implementing FAT32 itself was not all that difficult. It was getting the proofs of refinement and so on that was the longer thing that took multiple months. But FAT32, I will say, it comes with a nice specification, which is more than you can say with than most file systems. But Microsoft happens to have put out a specification for FAT32, and that actually is something that specifies at a bit and byte level what you should expect to see in a FAT32 disk image. So I was helped in that respect by having a technical specification available to me. And so yeah, I wouldn't say that. I mean, yeah, I would probably say that like there's one specific summer when I mostly knocked out a lot of the implementation of FAT32, but like everything that comes afterwards in terms of proofs of refinement and so on has been what's been like the more interesting part of this, honestly, than just writing some ACL2 code that represents FAT32. But
Mhm.
yeah, do I answer your question or is there something left?
No, no, yeah, it's just to have an idea. So, you mentioned something like a few months and then, several more months to get the proofs right? That's a summary if that's correct, which is nice. I think that, implementing something like this would actually take longer. So this was nice work. So,
Thank you.
yeah. Any more questions? So let's thank the presenter.
All
And
right,
we
thank
should
you.
move on to the next presenter. So, Neda.
Yes.
Okay, so we now have.
Sorry, I should have gone to the beginning of the talk. Can you hear me?
Yes.
All
So
right.
now we have Neda Syed Loy presenting optimization of timed scenarios.
Thank you. So first, I present the motivation of the work with a little bit of background material before I go to the contribution of this paper. So our ultimate goal is to synthesize a timed automaton from a set of timed scenarios. And our concern is that we want this timed automaton to be constructed in such a way that would allow efficient verification. And verification of timed automata crucially depends on the properties of automata, in particular, the number of clocks and the maximum constants with which the clocks are compared. And clocks are just some real valued variables that can accompany transitions. Essentially, a timed automaton is a finite state machine extended with a set of real valued variables, which are called clocks. And these clocks can be reset along with transitions and then can be read later on in order to make sure that the constraints between the two events in the automaton or two input symbols satisfy certain properties. So in our recent work, the work before this work, we were interested in specifying the behaviors of real-time systems. In particular, we wanted to specify all the behaviors that are allowed in a system with a particular sequence of events. And such behaviors must all satisfy the same constraints on the times between these events. So for this, we came up with the notion of time scenarios, which is a formal way of expressing such requirements, expressing all behaviors that are composed of the same set of same sequence of events, all of which satisfy the same constraints. For example, here is a example of a time scenario. In general, a time scenario is a pair of two components. E is a sequence of events, and C is a set of constraints. For example, psi1 is a scenario which is composed of 4 events, A, B, C, F, such that the time of these events satisfy 3 constraints. In particular, we want the time difference between event 0, which is A, and event 1 to be at least 2 units of time. Or similarly, we want the time difference between event 0 and the event 3, which is the last event, to be at most 5 units of time. And we are representing scenarios simpler, something that is more suitable for human consumption. In particular, we are in the box at the bottom of this slide. You see that we have a sequence of 4 events, and the labels like L0 and L1 are labels, and they can be interpreted as the symbolic representation of the time of these events. So L0 is interpreted as the time of event A. Similarly, L1 is interpreted as the time of event B, and therefore the constraint L0 greater than or equal to 2 accompanying event B means that we want in all the behaviors that are specified or allowed by this scenario, the time difference between A and B to be at least 2 units of time, for example. So now we define semantics of scenarios as the set of behaviors that are allowed by that scenario. For example, for Psi1, all the behaviors are essentially timed words that are known in the context of timed automata, which are sequence of events along with their times of occurrence. So the set of events, so the set of behaviors allowed by this scenario is A occurring at time t0, followed by B at time t1, C at time t2, and F at time t3, such that, first of all, the times of occurrences of these events is non-decreasing, and moreover, we have these constraints. For example, the first constraint says t1 minus t0 must be greater than or equal to 2, which means the time difference between B and A in all the behaviors that are allowed by this scenario must be at least 2 units of time. So I remind you in the remainder of the paper, I will use tau in order to represent scenarios, for example, represent constraints. I'm sorry. So for Psi1, the set of constraints, each constraint is represented as tau with some indices. In this case, tau 0, 1 means the time difference between event 0 and 1. Okay, we say a scenario is consistent if its semantics is not empty, otherwise it is inconsistent. For example, Psi1, our previous Psi1, this is a new scenario, is consistent because the set of allowed behaviors or the semantics of this scenario is not empty, while the scenario on the right-hand side is inconsistent because it is not possible to have sequence of events A, B, C, F such that the time difference between A and B is at least 2 units of time, and the time difference between A and F is at most 2 units of time. Therefore, we say Psi2 is inconsistent. So for a consistent scenario Psi, let's assume that the set of all behaviors that are allowed by this scenario consider those behaviors, and then consider the times between every event I and j in all such behaviors. And then we take the minimum of such time differences and we call it min ij. Similarly, if we consider all the behaviors that are allowed by this scenario and we consider the time distances between event I and j in such behaviors and take the maximum of them, we call them max ij. And obviously, the time distance between every event I and j must be within min ij and max ij. And then here we have this collection of 4 inequations. We refer to them as a golden equation. It specifies the relations between min ij and max ij for all the behaviors that are allowed by a scenario. For example, intuitively, the first inequation says that the minimum distance between event I and j plus the minimum distance between event j and k must be at most the minimum distance between I and k. So we propose another representation of the set of scenario, of the set of constraints of a scenario. For example, and we called it distance table. So for this scenario Psi, the distance table corresponding to that essentially is having sets of pairs between each 2 events. For example, here the constraint L0 less than or equal to 1 is represented in row 0, column 1 of the table. And we want that distance to be at most 1. And here we have 1 at row 0, column 1. And again, the meaning is that we want the distance between event 0 and event 1 to be at most 1 unit of time. So I should remind you that we name events beginning at 0. So event 0 essentially means the first event in the system. So as you see, distance table is just another representation for the set of constraints. And we say a distance table is stable if it satisfies 2 conditions. The first condition is that every pair in the table and every entry that you consider, the low value is smaller than high value. So I should have mentioned here that for every pair, For example, 0, 1 here, 0 is called the low value and 1 is called the high value. 0 specifies the minimum distance and 1 specifies the maximum distance. So we say a distance table is stable if it is valid, which means that every low value is smaller or equal than the high value. And moreover, we have the sequence of 4 inequations satisfied between all the entries of this table, and observe the close relationship between this inequation with our golden equation. And then we previously proposed this algorithm for stabilizing distance tables, in which we used these 6 inequations. For example, if it happens that in the table low ij plus low jk is not smaller than or equal low ik, then we can simply restore it by setting the value of lik to be lij plus ljk. And essentially we apply 6 rules iteratively until the table becomes either invalid or it becomes stable. So now here is an example. We have this scenario with its initial distance table. Observe that this distance table is not stable. Why? Because the high value between 1 and 4, between events 1 and 4, must be smaller than or equal the high value between 1 and 3 plus high value between 3 and 4. But that is not the case, because the maximum distance between event 1 and 4 is 11, and that is not smaller than the maximum distance between event 1 and 3, which is 4, plus event between 3 and 4, which is 4. 11 is not smaller than 4 plus 4. However, by applying our stabilization algorithm, we are able to make the table stabilize, and after that, we see that we will have all those 6 inequations satisfied in our table. In particular, now we will have the maximum distance between events 1 and 4 being smaller than or equal the maximum distance between 1 and 3 plus maximum distance between 3 and 4. Okay, so now what are the properties of a stable distance table? 3 important properties are that the stable distance table is unique for a given scenario. And moreover, each constraint that is represented by by entries of this distance table are tight, because as I said before, a distance table is essentially another representation for a set of constraints. Every entry of this table, let's consider row 1, column 4, so which includes pair 4 and 8. That represents 2 constraints. That means that the time distance between event 1 and 4 is at least 4 units of time and at most 8 units of time. So now the second bullet point here, it says that all the constraints that are represented by a stable distance table are tight. And finally, we say that if 2 scenarios are equivalent, then they are going to have identical stable distance tables. So now in our new work, we are interested in knowing what constraints are implied by other constraints. So given a scenario that is composed of some events E and set of constraints C, our objective is to replace C with an equivalent set of constraints C prime. We normally want C prime to be minimal, in the sense that removing a constraint from C prime would change the semantics of C prime. However, in general, a minimal set will not be unique, so one often has to apply various strategies to obtain one set that is most satisfactory according to some criteria. We obtain C prime by identifying those constraints that are implied by other constraints, and we either remove them entirely or we replace them with different ones. However, the linchpin of our approach is the notion of stable distance table. Means that given a scenario, we construct its distance table, we stabilize it, we obtain a stable distance table, and that is the beginning of our optimization. In the paper, we formally define the notion of implication, its transitive closure, and also the notion of support. Unfortunately, I will not have time to go over the details of them formally. There are some formal definitions involved. I attempt to show it here using an example. Let's say that I have this scenario with its stable distance table shown at the top. So as I said before, every entry of the table essentially represents two constraints. So in this stable distance table, we observe that 8 at row 1, column 3, specifies that the time distance between 1 and 3 must be at most 8. However, we observe that we have at row 1, column 2, we have the value 2, which means that the time distance between event 1 and 2 is at most 2. And similarly, we have that the time distance between event 2 and 3 is at most 6. So we observe that these two constraints implies the fact that the time distance between 1 and 3 must be at most 8. Similarly, the same constraint can be implied by a different set. The fact that the time distance between 0 and 3, event 0 and 3 is at most 10, and the time distance between event 0 and 1 is at least 2, implies that the time distance between 1 and 3 is at most 8. So we say that these two sets are supports for the constraint tau 13 less than or equal 8, or equivalently, these two sets imply this constraint. So now our algorithm starts with a stable distance table, obtained all the constraints that are represented by that stable table, and then tries to remove the constraints which have supports. This general algorithm attempts to decrease the number of constraints. However, it can be further specialized to decrease the maximum constants that appear in the constraints, and moreover, decrease the number of clocks in the resulting automata. In a minute, I will show you what I mean by resulting automata. But before that, a little motivation. Given a collection of scenarios, our ultimate goal is to synthesize a timed automaton whose language is the set of behaviors that are allowed by appropriate combinations of the scenarios. In fact, we have, this work has been completed and we have submitted the paper which was accepted. But that was our main motivation before we started optimizing the paper. And so for a timed automaton with k number of clocks, the number of clock regions depends on the number of clocks and also the maximum constant with which every clock is compared. And verification of a timed automaton can be computationally expensive, and the cost depends on the number of regions, means every attempt must be done to keep the number of clocks and the maximum constants as low as possible. And that was our motivation in this work. We wanted to use our general optimization algorithm in order to keep down the number of clocks and the number of maximum constant that are equivalent to time scenarios. What do I mean by that? So every time scenario like eta can be trivially converted to a timed automaton. So here I have eta at the on the left-hand side of the screen, and the time scenario corresponding to that is shown at the bottom. So observe that actually, so this is, yes, okay. So here we have event A, which with label L0 means we are interested in knowing the time of this event A, and we want event B to take place when at least 2 units of time has elapsed or at most 5 units of time. So we reset a clock along with event A, the clock is X, and then later on we read the value of clock on event B, and we want the value of clock be at least 2 units of time and at most 5 units of time. So the scenario on the right-hand side is equivalent to that, and we see that the timed automaton corresponding to that has only 1 clock. So the original one had 2 clocks because we had 2 labels, L0 and L1. Each of them will correspond to a clock. So clock X is reset along with event A, and clock Y is reset along with event B. And moreover, the maximum constant with which clock X is compared is 5, and the maximum constant with which clock Y is compared is 3. However, on the scenario on the right-hand side, there is only one clock, and the maximum constant of that clock is at most 5. So in the context of verification, the right-hand side automaton is better than the left-hand side. So given a scenario, our specialized strategies as following: we would like to replace C with an equivalent set of constraints C prime, such that if we create a brand new scenario whose set of events are similar as those in original psi, but the set of constraints are C prime, then the number of clocks in the automaton corresponding to psi prime may be smaller, but not larger than that for the original scenario. And moreover, the maximum constants corresponding to the clocks in A psi prime may be smaller, but never larger than those in the original timed automaton. So I show you the general strategy using an example. So I have this scenario psi 2 along with its stable distance table. And in our algorithm, our specialized algorithm, we order the set of constraints in decreasing order of constants. For example, tau 03 greater than or equal 13 has the maximum constant. And after ordering them, we in the second column, we show that what are the set of supports of each constraints. For example, tau 03 greater than or equal 13 has one set of support that is composed of two constraints, tau 02 greater than or equal to 9 and tau 23 greater than or equal to 4. After developing all the supports for constraints, we go ahead and remove them in the order that I just mentioned, as long as the scenarios have support. However, after each removal of a constraint, we must go ahead and update all the supports in which this particular removed constraint appears. What do I mean by that? For example, after removing the first constraint, tau 03 greater than or equal 13, we observe that that constraint appears in a support set of tau 23 greater than or equal to 4. I'm talking about the second constraint from the bottom in the table. So now, in the support, we have to replace that constraint, the removed constraint, with its original supports. Means that now tau 03 greater than or equal 13 is going to be replaced by the support, which is tau 02 greater than or equal to 9 and tau 23 greater than 4. But the moment that we do that, we observe that the constraint whose set of support is updated now loses its support, because the constraint appears its own support. And this is not allowed. In particular, a constraint cannot support itself. So we go ahead and we remove the constraints in that order as long as they have supports, and we update the supports. And at the end of this phase, we are left with 3 constraints which do not have, which still have supports. And these constraints are shown at the bottom table, and then we go ahead and remove them one by one, and at the end we stop when there is no constraint with any support. Means that we cannot remove any more constraints. As a result of doing that, we started with psi 2 on the left hand side, and we ended up with psi prime 2. Observe that the automaton corresponding to the original scenario requires 2 clocks with maximum constant 11 and 9, whereas the scenario we obtain after this specialized strategy requires only 1 clock with maximum constant 9. Next, I want to quickly compare our work with difference bound matrices, or DBMS. DBMS are an efficient technique for representing clock zones in the context of verification of timed automata. It turns out that DBMS are essentially equivalent to our distance table. However, in the context of time scenarios, our optimization performs better than the DBM reduction technique. What is DBM reduction technique? Essentially, it is an optimization technique that minimizes the number of constraints, only the number of constraints. Moreover, our approach is simpler and more intuitive. Here I have included the result of comparison between our method and the DBM reduction method on 3 scenarios. Let us take the first scenario, Psi1. The original scenario has 4 constraints, and in the timed automaton corresponding with this scenario, we will have only 1 clock with maximum constant 10. After applying our method, the number of constraints is still 4, but the maximum constant goes down from 10 to 6. However, in the DBMS reduction technique, there are 2 generated scenarios, one in which the number of constraints is still 4, but there are 2 clocks with maximum constant 6 and 2. And in the other case, the number of constraints is increased to 6, and there is only 1 clock with maximum constant 10. You see that both these outcomes are worse than our outcome, because the first outcome increases the number of clocks, the second outcome increases the number of constraints. So to conclude, in this work, we have proposed a general algorithm that can reliably optimize scenarios according to different strategies that intended to achieve different goals. We have proposed a particular strategy which minimizes the maximum constant, but also tend to decrease the other constants, as well as the number of clocks that would be needed after converting a scenario to a timed automaton. And it turns out that in the case of scenarios, this optimization perform better than the DBM reduction technique. Thank you.
Okay, thank you, Neda. And we have time for a few questions. And while there's one here. So it's mentioned by me here. This is not a question, so perhaps leave it after the real questions, but let's go ahead and do it anyway.
Okay,
We wrote some timed automata related code using DBMs, and would be really happy if a new method comes to replace DBMs by being more efficient. So let's hope it does. A few questions here from Gustavo. If you've tried to apply this method and measure the actual gain in terms of verification time.
In terms of verification time, actually no, because we have not done the experience, because it's a well-known fact that the number of clocks and the maximum constant with which the clocks are compared directly affect the cost of verification. So it's a well-known fact. We didn't actually go and see that, you know, in these small examples, how much gain we obtain. But I should mention that these are just, in this work, we were trying to essentially build the building blocks of our work, because the timed automata that I showed in this work are very trivial. But as I said, our motivation is to build a scenario from a set of constraints. And we want to apply this work to that context. Means that we are not dealing with just one scenario, but a set of scenarios where we are going to deal with possibly more clocks, and knowing that number of clocks in general affect the cost of complexity. If we decrease the numbers, we know that we have gained, but how much exactly we have gained, we have not measured that.
Okay. Another observation from Rodrigo. I haven't had a lot of contact with timed automata, so this talk was incredibly interesting for me. Thank you, Neda.
Oh, thank you.
Okay. And I have a question as well. You mentioned, I was going to ask if how did it compare to DBMs, and you explained it to us. But you mentioned that it's more efficient than DBMs. But
in the context of time scenarios.
Yes, I know.
DBM is more general than our work. Indeed.
Ah, okay, okay. Yeah, but my question is, because you mentioned that your approach, it minimizes the number of constraints, the maximum constants, and the number of clocks. You can fine tune it to do either of those.
Mhm.
While DBMs only minimize
Number
the
of
maximum
constraints.
constant,
The number of
number
constraints.
number of constraints. Yes. So does your method, is it more efficient than DBMs if you only optimize by the number of constraints, or is it the same thing?
So in the context of time document, the reason we say it's efficient because it cannot, in order to apply DBM method, we have to convert scenarios to time dosimeter, and we have to introduce new clocks, make sure that every event is accompanied with a clock, because we are interested in measuring the time between every two events. A time datometer in general might not have clocks on every two transitions, on all transitions. But in order to be able to apply DBM method, we have to introduce some artificial clocks that are not used, but they are just introduced in order to measure the time between every single two events. And in that case, it is not very intuitive, not very easy to apply the method. So our method can be applied directly, simply. In the context of time, datometer is more efficient and simpler. But in general, DBMS can be applied to more general cases, and we are not saying
Okay.
there.
Well, if you apply it to an interesting and important case, that's what matters, right? Okay, so thank you. And I have another question, and the question is, which one do you think is going to be more, a more increase in efficiency, reducing the number of constraints, number of clocks, or the constant?
Increasing the number of constraints is not a concern in this context. For verification of time datometer, we are not concerned about the number of constraints, but we are concerned about first, number of clocks, second, the maximum constant. Because if I go back to that equation that I just showed you, the number of regions, you see that it is exponential in the number of clocks. So it is better if our priority is to decrease the number of clocks first, and secondly, we want to decrease the maximum constant with which clocks are compared, because the equation says that the number is exponential in number of clocks.
Okay, that's interesting. That's very nice. Yeah, this is very nice work. I mean, I've always tried to avoid timed automata just because of the complexity of representing all of these clocks and all of these regions. So I think this is very important work, and I congratulate you on that. So thank
Thank
you.
you so much.
Okay, I see no other questions, so perhaps we can end the session and thank the speakers. It was a very interesting session.